Hello, and welcome to my talk about zero knowledge and about SNARKS. This third part, I will be talking about the application of polynomials in computer science. And I will be using three different examples: secret sharing, error correction, and error amplification, which is sort of an introduction into the fourth part, which relies heavily on polynomials. So I think these examples is an interesting way to learn about the use of polynomials. So the first idea, the first protocol I want to discuss with you is called secret sharing, in which we have threshold secret sharing, meaning that there is a quorum of, let's say, 3 persons that can reconstruct a secret. So we will divide the secret among, let's say, 5 persons, so that any subset of 3 persons can reconstruct the secret. What we will do, we will use a polynomial of degree 2. Why is that? Well, because with 3 points you can reconstruct a polynomial. So what we do is the following: the secret will be located when the x equals 0, so it's the f of 0. So this will be the constant, the c of the polynomial. The other 2 coefficients of the polynomial, a and b, we choose it at random. And then what we do, we distribute the shares by giving out points of the polynomial. So it looks a bit like this. On the left you see the f of 0, which will be the secret, and 1, 2, 3, 4, and 5. These are the shares that will be given out to the different participants. So what's the idea? I said 3 points determine completely a second degree polynomial, so any 3 parties can reconstruct f and therefore compute the secret, which corresponds to the f of 0. But if we do this over the real numbers, this will not work, because the problem is that we want to choose the a and b at random, but this is not well defined using the real numbers. So instead, what we will be doing, we'll be using a finite field. And in our example, we will be using 17, which is just a convenient small prime number for this example. Now, if you look at this slide, you will realize this is the polynomial that we will be using, modulo 17. Okay, so first let me say that using a prime number is not a problem at all, because polynomials they need addition and they need multiplication, and these are all well defined over a finite field, including division, right? Division actually is defined as multiplication by the inverse, and each element has an inverse modulo any prime number. And the second thing that you should note here is the lack of continuity, right? Polynomials or any function over a finite field, the notion of a continuous function doesn't make sense. So what we see here is that even though there is some deep structure as defined by the polynomial equation, it looks almost completely random to us. Okay, so this is something that you should keep in mind. Our intuition about polynomials over real numbers does not apply to finite fields. Okay, so let's go on. So as I said, the secret we will be distributing will be the number 13, and we choose the coefficient 2 and 10. They were random numbers, modulo 17, so this gives me the polynomial. So on the left we see the secret is 13, f of 0. We compute the other 5 shares and which we hand out. So now to convince you that secret sharing works, we'll be reconstructing the original secret from the parts from the shares S1, S3 and S5. And we'll be doing this in 2 different ways, which is interesting for various reasons. Or just before we do that, 2 cooperating shareholders cannot find the f of 0. All possible values in the finite field are equally likely. And so this is the property that is true over a finite field and is not true over the field of real numbers. Any 3 cooperating shareholders can find the f of 0, and we will show this now with participant 1, 3 and 5. So the first method is simple. What we do, we know that we don't know A2, A1, A0. This is what the 3 shareholders want to compute. So, but they know these equations. So the first shareholder, well, he knows that the x is equal to 1, so he can fill this in the polynomial, and he knows it's equal to 8. So the 1 here is x squared, the 9 here is 3 squared, and so the 8, well, the 8 actually is 25, is 5 squared, so it's 25, modulo 17. So this is why we get 8 here in this position. And so we now have 3 equations with 3 unknowns over a finite field. We can do Gaussian elimination, and we can find the secret, the coefficients A0 equals 13, A1 equal 10, A2 equal 2, and so we know that the secret is indeed 13. Okay, so this is one method. So there's another method which is very interesting, which is called interpolation by Lagrange. Lagrange interpolation gives us a ready formula for computing the unique polynomial that goes through 3 given points. In our example, it's 3. So suppose we have 3 points, A1, B1, A2, B2, A3, B3. We are going to construct a polynomial which goes through these 3 points. But we're going to make this construction in 3 parts. We're going to construct a polynomial F1 which goes through A1, B1. So how do we do this? Well, if you look at this, so this has in this product, it has all the points, all the x values of the points, except the A1. And now, what happens if you substitute A1 in this polynomial? Then this factor we get A1 minus A2, which is divided by A1 minus A2. So this gives 1. This second division here on the right also will give you 1. So this whole fraction will give you 1, which means that if you substitute x equal to A1, the result will be exactly B1. So this is one property that we need. We will also need another property, because we're going to add up F1 with F2 and F3 on the next slide, and we don't want F1 to complicate things. So what we are doing, the definition of Legendre will make that if we substitute A2 in this formula, well, in that case, this factor will be 0, so the whole value will be 0. And the same is true if you substitute x equal to A3, this part will be 0, so the whole product will be 0. So this is good. Why is this good? Well, because we do the same thing for the point A2, B2. We do the same thing for the point A3, B3, and we will sum up these three polynomials. And so if you look now at the f of A1, well, so the f of A1 is equal to B1 in f of 1, but it's 0 in the other two positions. So the result will be A1, B1. And the same is true for the other 2 points. So we see that this polynomial, which is the sum of all these three partial polynomials, indeed goes through the points A1, B1, A2, B2, and A3, B3. So this is nice. Also note that the degree of the polynomial by construction, any part has degree 2, so the sum is also of degree 2. So we know it goes through these 3 points. We know it's of degree 2, so by definition we know it's the only polynomial that goes through these 3 points, as is stated here. In our case, we had the example with the secret sharing, so we can substitute A1, B1 is the pair 1, 8. The third point had these coordinates. The third point has those coordinates. And so we use Lagrange, which gives us this formula. Well, instead of calculating this, we can actually use a shortcut, because by setting x equal to 0, we will find our secret. So we substitute x equal to 0, so we get -3 here and -5 there, as you can see here. We do all these computations modulo 17, and this will result in 13. You can even, there are some additional things you can use to check. The important thing here to note is that division, I mentioned this earlier, division in this case is the same as multiplication with the inverse, and we can compute the inverse using Euclid's extended algorithm, which is a sort of standard way to do this in case your prime number is large. In case it's small, you can do by trial or error or use a table. So we showed Shaming secret sharing. This is how this protocol is called also. We showed it for five parties, but we could hand out more shares to more parties. But the limit that we have, of course, is that it must be smaller than the field size. In the remainder of this talk, I will talk about this prime number, which is very interesting because it's prime. It's actually a Fermat prime, and it has a very, very good binary representation. It is true that finite field exists for every power of 2, but the arithmetic of this is slightly more complicated, and it's beyond the scope of the lecture. For a true understanding, it doesn't make so much of a difference. So, generalizing Shamir secret sharing, we have m parties, m shares. We reconstruct the coarm that we define is n+1, because this is the number of points that we are going to need to reconstruct a polynomial of degree n. So this slide describes the general description of how to apply secret sharing for general parameters. So let me summarize some of the properties of polynomials. A polynomial is a formal object of the form a1 an xn plus 1 well, so on, a1 to the power x1 plus a0 to the power x0. Okay, so this is the formal object. We can represent a polynomial by specifying these coefficients, a0 up to till an. Another way, we just use this fact of specifying a polynomial of degree n is by having any set of n plus 1 points. Okay, so any set of n plus 1 points also uniquely specifies a polynomial of degree n. And so some terminology, going from one representation to the second representation, we call that evaluation. Going from 2 to 1 is called interpolation, and Lagrange interpolation is a specific case of that. Now, you maybe know that there exist fast algorithms for switching between these two representations, which is called the discrete Fourier transform, which is like a cousin of the ordinary Fourier transform, which is over the field of complex numbers. In this case, the underlying field is a finite field. And by a clever choice of the values of the domain from x0 to xn, you can have an n log n algorithm for this. Why is this important? Well, it turns out that the switching between these two representations is often needed in SNARKS, so the complexity of the Fourier transform is sort of a bottleneck for this algorithm. Okay, so now I will explain to you a second application of polynomials, which is error correction. And I'm going to give you an example. What we're going to use, we're going to have 8 symbols, which are elements of our finite field. And what we are going to do, we're going to expand a polynomial of degree 7 over a larger interval. So the original definition is from 0 till 7, but we're going to expand it from 0 until 39. And I'm going to show you a program. I have here some Jupyter notebook. I import Galois package and import a random package. Just to show you how it works, I'm still giving you the secret sharing example. So here in this part, I define the finite field of 17 elements. Here we have these 3 participants, 1, 3, and 5, with their respective values, 8, 10, and 11. And we just use the function for Lagrange interpolation, and we indeed get back the polynomial that we wanted. So this goes back to the secret sharing example. Now we are going to the new example, so I have to redefine the finite field with this other Fermat prime. Here I define the initial range from 0 till 7. I just pick a random message. Right, I generate 8 message symbols completely at random. I do Galois, I do Lagrange interpolation, and we obtain this polynomial. And then what we do, we are going to expand this polynomial over the range from 0 till 39. So we obtain this long list of 40 symbols. You can see that the first 8 elements are equal, but the other elements are different. So this is a way of coding a sequence with 8 symbols into a sequence with 40 symbols. And now it's clear that by the same theorem that we had before, any subset of 8 of these values will give you back the polynomial. So this is the idea of using error correction. We have, in this case, we had 8 original message symbols. We were adding 32 redundancy symbols, getting for an overall total of 40, and then any subset of 8 symbols will allow us to reconstruct the polynomial and reconstruct the message. So this is this technique. In general, we can, I choose these values because they are small enough to fit on the screen, but it's completely flexible. You can choose your message data from 0 till n, and you can expand the domain, extend the domain for any value you like, as long as below the field size. And we can do error correction. Actually, there are 2 kinds of error corrections. The one that I explained to you is called erasures. There's actually an even more sophisticated error correction. If you do not know, you can have errors, but you do not know where the error is. Now, in that case, you can also correct the error, but then for every erroneous point, you will need at least 2 correct points. So this is known as the Berlekamp-Massey algorithm, but otherwise not subject of this talk. So this whole scheme is known as Reed-Solomon coding. So using polynomials to encode information is known as Reed-Solomon coding, which is used, for instance, in our CDs, our DVDs, in QR codes. It's also been used in the first NASA space missions. And now we are going to the application that really interests us, which is error amplification. To explain this to you more clearly, I will go back to the Jupyter notebook. So what I'm going to do now, I'm going to take this sequence, but I'm going to make one minor modification. I will be adding 1 to the 4th element here, so you pay attention, it ends in 7-2. I add 1 to it, and now it gets 7-3. I will do again Lagrange interpolation. The first polynomial was called f, now the new version is called g. And what happens is this: I get a completely different polynomial. Okay, so you can compare that if you want. The polynomial is completely different. And what we can do is we can ask the question, so at how many x's do we have that the f of x equals to g of x? So the polynomials are the same values. So I wrote here a Python script which will test over the whole finite field of 65,000 elements whether the g of x equal to the f of x. Well, the variable is called I in this case, but that doesn't make a difference. And what we see is very interesting, because what we see is that only on the original point that we know they are the same. Remember, I on purpose, 3 is different in this situation. So only on the pre-agreed values of x, these 2 polynomials are the same. On all the other values, these polynomials are different. And so this will allow me a fast way to compare polynomials. Because if I take any value now in the larger interval, it's a proof that f and g are different. So this is the property that we are interested in. This is the property that SNARKs are using to obtain fast proofs. So as I explained already, if we change 1 bit of y, then the interpolating polynomial g will be completely different. So also the extension polynomial over the larger domain will be different. So as a consequence, the redundant values will vary widely and will be different from the corresponding x, the original values. So it's important to know that we are extending the 8 to 40, so this is known as the blow-up factor. In this example, it is 5. But again, instead of extending just to 40, we can extend until over the whole field. So extend up to 6,500, 537. And this is the idea which is applied in verifiable computing. In order to catch a dishonest prover with little effort, the verifier tests on the extension domain D whether these two polynomials are the same. So we can have a specific example of that, comparing strings using polynomials. So suppose Alice and Bob have two strings y. Alice has y, Bob has z over our finite field, and they want to compare using polynomials. So Alice claims that y and z are equal, and Bob wants to check. So how can we do this? Well, as suggested before, Alice computes the unique polynomial f of degree n interpolating over the n+1 points, which defines the extension f tilde over the larger domain. Likewise, Bob interpolates his polynomial over his points z0 up till zn. Now, so if y and z are identical, then the polynomials are identical, but if y and z differ at only 1 bit, then these polynomials are very likely to be completely different. So what Bob now does, it chooses a random x over the extension domain and asks Alice to send the corresponding value f tilde of x. And now Bob is going to compare the f tilde with g tilde at the location x, and if the two values are the same, then Bob believes that y and z are equal, but if not, then Bob rejects, because then he knows for sure that that y and z are not equal. So the question that we now ask is the soundness question. What is the probability that Bob accepts if in fact y and z are different? And this is an easy corollary of what the properties of polynomials that we have discussed before. Because suppose that Alice claims that f interpolates over y, whereas in reality this is not the case. Then we know that the extension polynomial g tilde and f tilde, they must be different. So we know that they can agree on at most n points, because if they agreed on n+1 points, they would be equal. So by using this property about polynomials in that n+1 polynomials define a polynomial of degree n, we can easily derive this equation. So the probability that they are different must be below 1 minus n divided by m, where n is the degree of the polynomial and m is the size of the extension field. And so by choosing the size of the extension to be very large, we can make this probability of arbitrarily small.